All right, we're going to go through chapter 24 homework. I'm going to go to 2425. All right, so you've got uh, a RNA sequence translated from left to right. So we've got CUA, UA, UCGA, GGA, CAU, CG, and then UGA. All right, so here is your messenger RNA. All right, you know it's RNA because you have uracil in there. When you have a U, you know that is an RNA. If you have a T, then you know that's from DNA. All right, and so we want the amino acid sequence. All right, I'm going to do more than that. I'm going to say what DNA sequence did that come from? And then what transfer RNA anticodons were used to bring in that amino acid. All right, and so your codons are a triplet pair of your off of your messenger RNA. And so we're going to have our chart, and we're going to find the amino acid that goes along with these codons. All right, so we will have on the test, we will have this chart on the test. And so CUA, all right, so C, U, and A is leucine. All right, so you're going to look up each one of these and put them in. All right, so CUA is leucine, and then you got to find UAU. I'm not going to do all of these. You just have your chart, and you just look at UAU. All right, so UAU, so that is right here, tyrosine. All right, so you're just gonna, then you look at this one on the chart, and you write that. You find this one on the chart, you write that amino acid. So you don't memorize anything, you just look it up on the chart and put in the symbol or the name for the amino acid. The key is the codons are for the messenger RNA. All right, so the DNA that it came from, so your base pairs for DNA are GC, and the base pairs, and remember, the base pairs for GC have 3 hydrogen bonds. And then TA has 2 hydrogen bonds. Now, when you're looking at your RNA, then you still have the same GC, but you have UA. So GC, now you have U and A as your base pair. So the DNA, all right, so this was G, and then the RNA base pair C. U is from A. All right, so your A came from T. Remember, there's no U in your DNA. All right, and so U and A are the base pairs. A and U, except this is DNA, so that's T. All right, then U, A, and then a G, and then a C, and then a T, and then a C, and then a C, and then a T, and then a G, and then T, and then A, and then T, and then G, and then C, and then A, and C, and then T. All right, so this is your DNA sequence. Note that there are no uracils, all thymine, so no U's, all T's from the DNA. So this is the DNA that the messenger RNA was coded from. All right, and so these are the codons. And when you look at the chart and you see what it says it is, usually it says it's a codon chart, but this is a codon chart. All right, so if you get down into the small print, it says these are the codons. Usually it says it bigger on the top. All right, and so it is the codons. The transfer RNA have the anticodons. And that's what brings in the correct amino acid. So the anticodons, all right, so now again, we're RNA to RNA, no T, all it's going to be U, not T. So you have G, and that's your base pairs for your RNA right here. All right, so C, you got G, U, you got A, you got U. So this is the anticodon that brings in the amino acid. But the chart is a codon chart. You're looking at the messenger RNA, the codon chart. You will have the wrong answer if you use the transfer RNA anticodons. It's not an anticodon chart. It is a codon chart. All right, and so the next RNA, you got A, U, A. That's the next transfer RNA anticodon that brings in that amino acid. Then you got your G, C, U. You got your C, C, U. You got your G, U, A. You got your U, G, C. You got your A, C, U. These are your anticodons, and each one of these is a transfer RNA that brings in the correct amino acid. All right, so you have to be able to recognize DNA. Anytime you have thymine, it's going to be DNA. Then you have to be able to translate that to your messenger RNA, which then you have to be able to know the anticodons that have the transfer RNA that bring in that amino acid that you get from the codons. All right, so I'm not going to finish that one. You just look up the other 1, 2, 3, 4, 5 codons and put in a symbol or name for the amino acid. All right, 28. PVC. All right, so this is an addition polymer. So they give you the formula of PVC. PVC is polyvinyl chloride. All right, and so this group is called the vinyl group. You don't need to know that, but that's the reason why it's called vinyl chloride. And then when we polymerize it, it's called polyvinyl chloride. All right, and so you have an alkene. An alkene is going to make an addition polymer. Addition reactions are what alkenes do, and so when they polymerize, they are addition polymers. All right, so you simply break the double bond, and you know carbon has to have 4 bonds, and so then you stick a bond out to the left and out to the right, and then you put a bracket, all right, and then you put N, which is a large number. N is a large number of these. We are going to polymerize it, and then your single bonds all remain the same. So the only thing you do is you break the double bond, and then you put a bond out connecting to another, because what does that mean? Well, that means that you're connected to another molecule of vinyl chloride. And that means you're connected to another molecule of vinyl chloride. And that means it's going to go on forever, or not maybe forever, but a large number of times. All right, it's just going to keep repeating. It is a polymer, and so this is vinyl chloride. And so this is polyvinyl chloride and PVC. Sewer pipes are made out of PVC. All right, the next polymer on 2430 is a condensation polymer. So it has a C double bond O, CH2 sub 10. Then it has a C double bond O, and then an NH bonded to a CH2 sub 6. And then another NH, and then a C double bond O, CH2 sub 10. So now it's repeating. We're doing repetition, and then a C double bond O, NH, CH2 sub 6, NH, and then it keeps going this way and the other way. All right, and so what we see is we're going to have a compound that has 2 carbonyls, and we're going to have another compound that has 2 amines. And so those are the 2 monomers, and this is a condensation polymer. And so it's going to lasso water. And so we're going to put we're going to do hydrolysis. We're going to split it with water. We're going to put the OH on this side and the H on this side to make a carboxylic acid and an amine. All right, so anywhere where you see that, you're going to put an H on the N, and you're going to put an OH on the C double bond O. Hydrolysis, split with water. We're going to put an H on the nitrogen. We're going to put an OH here. And so we are splitting this with water. We are splitting this with water. We're going to add water across that bond. All right, and if you see what 2 molecules that you keep making, it is this dicarboxylic acid and this diamine. And so your 2 monomers, NH2, CH2 sub 6, NH2 is the 1 monomer. You use N large number of times, and the other monomer N large number of times is your carboxylic acid with CH2 sub 10 in the middle, and then another carboxylic acid. And so again, to make this, you simply lasso water to make your condensation polymer. All right, so if you lasso your H2O, you bring that together, and over here, you would lasso your H2O. The H comes from the N, and the OH comes from the carboxylic acid. Your NH here. You have your lasso of water. All right, and so the 2 monomers are the diamine and the dicarboxylic acid. All right, so the same way you make them, lasso water, you have to break them. You do what is called hydrolysis. You break that and add water. Splitting with water is hydrolysis. All right, 2434. All right, valine has the structure. All right, so they give you the structure of valine. It has CH3, CH, CH3. That is then connected to the chiral carbon where it has an H, an H2, and the carboxylic acid. All right, and so it says draw the zwitterion at pH neutral. So your neutral, so you have 3 basic amino acids, you have 2 acidic amino acids, and then you have 15 neutral amino acids. And so the pH here is going to be 6. So your neutral amino acids have a pH of 6. And so your acid is a little more powerful than your amine base. And so the pH is slightly acidic. When you're looking at the basic amino acids, you're looking at a pH of about 9. And when you look at the acidic amino acids, you're having a pH of about 3. So acids 3, neutral 6, base is 9, so they increase by 3 each time, going from acid to base. So that's an approximation. They're not exactly 3, 6, and 9, but that is a good approximation. Yes. All right, so your zwitterion it means dipolar ion. And so we are going to have the acid is a proton donor, the base is a proton acceptor. And so we have CH3, CH, CH3. And now after we did our internal acid base, now we have here NH3, and that has a positive charge. And here we have a C double bond O with an O minus. And so this is a pH 6 neutral amino acid. If we want to look at a pH of 3, that means that we are acidic. And so if we are adding H plus, then we're going to have an acidic solution. So you put it in HCl, any acid, get the pH down to pH of 3. And what's going to happen is the O minus is going to take the H plus, and you're going to have CH3, CH, CH3. The NH3 is still positive, but now you have a carboxylic acid. All right, and so your overall charge in acid is going to be positive. And so this has an overall charge of +1. This is neutral. Now, if you stick it in base, so you stick it in sodium hydroxide, the OH minus is going to take off your acidic hydrogen here. And then you have your back to your NH2 here, but you still have your O minus here. All right, and so the OH minus took off this H, and over here, your overall charge is minus when you are at a pH of 9. And so your amino acids, 15 of them, the neutral ones, they are neutral at pH 6. They are going to be a +1 at pH 3. They're going to be a -1 at pH 9. All right, 2442. How many hydrogen bonds link A to T? And that is 2. All right. A to U, also 2. And then C, G. C to G is 3. All right, so your hydrogen bonding is the same here. So the same amount of hydrogen bonding between A and T and A and U. It is the same amount of hydrogen bonding. And C to G, you have 3 hydrogen bonds, so it is more strongly more hydrogen bonded. So it is a stronger interaction. It has 3 hydrogen bonds holding it together versus the AT or the AU, which has just the 2 hydrogen bonds holding it together. So when you have the dots between those letters, that is indicating hydrogen bonding. All right, and so you have hydrogen bonding 3 times here. You got hydrogen bonding 2 times here, 2 times here. The dots between them indicate the hydrogen bonding. All right, 48. Write the amino acid sequence obtained from left to right, messenger RNA. All right, so this is the exact same problem that we started with. Good for you to practice AUU. Then you've got GGC. And then you got GCG. AGA. CG. AAU. Doesn't have to be this long. Okay. GAG. And then CCC. And then finally AGU. All right, so you're going to find 1, 2, 3, 4, 5, 6, 7, 8, 9 amino acids from the chart. You simply find AUU, write down the name of that amino acid or the symbol for that amino acid. You find GGC, you write down the name or the symbol. So AUU, we can do the first couple, but this is just finding your chart, using your chart. All right, so right. So we have AUU. All right, first letter AUU. All right, isoleucine. So you would write isoleucine. GGC. GGC. So here's G, here's G, here's C. Glycine is the second one. Then you have GCG, G, C, so GCG right here. Alanine, you would write, and then so forth and so on. You got AGA, so you got A, you got G, you got AGA, arginine. All right, so you would just go down the line. It's a very simple process to do that. Again, you're going to be given this chart in order to find your sequence. The only thing that you have to make sure that you remember when you're doing this is a codon chart. That means you're getting your codons from your messenger RNA. They may give you a transfer RNA and ask for the amino acid that comes with this transfer RNA. Remember, this is RNA, this is RNA. You got your G going to C, you got your A going to U. So this is UAA. And so if they're looking for the amino acid that goes with UAA, you don't use the chart. The chart is for codons. Transfer RNA has the anticodons. So then you have to convert that to AUU. That is now the messenger RNA. That is now a codon. All right, so this is messenger RNA, triplet pair. This is your codon. This is what is on the table. All right, so it's very simple, but if you see transfer RNA and you look up UAA, that is not the correct amino acid because it is not an anticodon chart. It is a codon chart. AUU is the correct amino acid that you would get from the chart. All right, it could ask what DNA sequence did this come from? Now up here, you got your same GC, but now you've got your A and your T. You have no U. So A goes to T if we're looking at our DNA sequence. And then U goes to your A. And then G, C, C, G. Okay, you can continue on down the line. So when you're looking at your DNA, you're going to have your thymine and no uracil. So that's the same as the first problem that we did. All right, 49. So 49 is more specific with your anticodon. So it could say it could say your anticodons are GAC, UAC, AAA, and CAA. And it could say, here's the anticodons. What are the amino acids? All right, and so you would have to know that anticodons means they're giving you the triplet pair on your transfer RNA. In order to get your messenger RNA and the codons for the chart, you know that you have to do the base pairs. Again, G, C, and U and A. So G, C, A, U, C, G. All right. So you're looking up C, U, G, and you're looking up A, U, G, and you're looking up your U, 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 and you're looking up your G, U, U. These are your 4 codons. This is the chart. So when you want to find your amino acids, when the anticodon is GAC, you're looking for the codon CUG. So CUG, CUG is leucine. So that is leucine. Note, if you looked at the GAC, the GAC, you would put aspartic acid. So again, that is the only reason why people miss this problem. They will use this as an anticodon chart instead of a codon chart. Right? That will give you, of course, the wrong amino acids. This is a codon chart. You have to use the codons, and the codons are from your messenger RNA, not the anticodons, which are your transfer RNA, which brings in the amino acid. But it knows which one to bring in because the anticodons match perfectly to the codons on the messenger RNA. All right, and so then 2450 is just the opposite. They give you the codons and then they ask for the anticodons. So your 2450, it says here are your codons, and that's UUG, CAC, ACU, and GAA. All right, so now you know that's the codons. You simply go right to the chart if you want the amino acid that goes with these codons. All right, the question was, what are the anticodons? Again, GCAU. All right, so AAC, GUG, UGA, and CUU. All right, so again, you're going to look with the amino acids, because this is usually all in the same question. So the question is going to be, well, here's the codons. What are the anticodons? What are the amino acids? Okay, and it may ask it in that sequence because the anticodons, that's what's bringing in the amino acid, but the chart is a codon chart. So this is where you get the amino acid that's coming in. Again, there is no reason why you wouldn't have an anticodon chart, except I've never seen one. All right, they are all codon charts. They have agreed that we're going to do codon charts and not anticodon charts. So you're looking at the base sequence from your messenger RNA, not your transfer RNA. So your messenger RNA has the codons. Your transfer RNA has the anticodons. So this is your transfer RNA, and this is your messenger RNA. All right. 2453. Write the structural formula for the addition polymer made from a trans 1,2-dichloroethene. So again, they wouldn't have to tell you it's an addition polymer. As soon as you see that you have an alkene, alkenes do addition reactions. And when they polymerize, they form addition polymers. And so this is exactly the same as the last one, where anytime you have an addition polymer, you get rid of the double bond, and then you have to have 4 bonds to carbon. The single bonds do not change. You just put in all the single bonds, and that's just going to keep repeating. They said trans and cis. Okay. So this is cis, 1,2-dichloroethene. All right, so they wrote the word trans and then they drew the cis conformation. And so this is simply, you write the word poly. So you polymerize it by adding n amount of that and n amount here. N is a large number. This is a poly cis 1,2-dichloroethene. All right, if they wanted to have the problem done correctly because they said trans, maybe they should write trans. All right, so this would be the trans 1,2-dichloroethene. And you have a large number of these molecules, so you polymerize it again, you break the pi bond, all of your sigma bonds are intact, and you just write down all of your bonds, and then you put a bond out each direction, and N, again, that's a large number of times. What does that mean? It just keeps repeating, so you just keep repeating. You got your H, Cl, you got your Cl, you got your H. That's another molecule of that, all right? So then another molecule comes on, H, Cl, Cl, H, and then another molecule comes on. So just keeps repeating many, many, many times. And so you simply put a bracket where it's repeating and you write N. All right, and so this is poly, and then just the name of the alkene. So you just simply put the poly in front. It's a little misleading because it still says dichloroethene. It has not got a double bond. It is a polymer. Why it says poly out in front. So poly, trans, 1,2-dichloroethene. So it does say ethene because that's how you name a polymer. You name the polymer by simply putting poly in front of the monomer name. So this is the monomer, and this is the polymer. To name a polymer, you simply put the word poly in front of the monomer name. All right, 2455. All right, Kevlar polymer fiber used in bulletproof vests. So here is the polymer Kevlar. So we have a C double bond O, and that's to a benzene ring, and that's to another C double bond O, and then your NH, which is bonded to a benzene ring, and then an NH bonded to a C double bond O, bonded to a benzene ring, to another C double bond O, NH, benzene ring, NH. All right, so it keeps doing the same thing over and over and over. All right, and so again, we are looking at a polyamide. All right, so you still have to know that you have what functional groups that you have in each one of these, and that is an amide functional group, and it's a polymer, and so that is called then a polyamide. And polyamides are nylons, and they are also Kevlar. Right? And so here, just like we did last time, we're going to break this bond using water. That's called hydrolysis. The C double bond O, that gets your OH of the water, and the N gets the H of the water. All right, anytime you see your amide, you're going to hydrolyze it. The N gets the H, the C double bond O gets the OH. Anytime you have an amide, you're going to hydrolyze it. The carbonyl, C double bond O, gets the OH, and the N gets the H. And so then you can see your two monomers, this dicarboxylic acid and this diamine. And so your two monomers to make Kevlar are NH2 with a benzene ring and NH2. That's the one monomer. And the other one is a carboxylic acid with a benzene ring and another carboxylic acid. Right? And so you have N number of each one of those. So a large amount of that, a large amount of that. You polymerize it. You lasso your water. And so you have your N, which is going to lasso one of the H's. And then a benzene ring. N, going to lasso one of the H's. Carboxylic acid lassos the OH, benzene ring. Carboxylic acid lassos the OH. And so this is the repeating unit, the Kevlar. And then, of course, you would get N number of water. So a lot of water is being released because you're lassoing water. All right. 56 is nylon 6. So 24.56, this one is nylon 6, all right, and it has the following structure. So nylon is a polyamide, all right. In this case, they give us NH. So we're going to lasso an H off of that, and that's why it has a bond there. Going to bond to usually a carbonyl. Then CH2 sub 5. All right, but not another N. This time it's the carbonyl. Then your NH, and then CH2 sub 5, and then a carbonyl. All right, so when you want to find the monomers here, again, you find the functional group. This is a polyamide. So nylons are polyamides. And so every time you see an amide bond, you're going to hydrolyze it, which means you're going to break it with water. The carbonyl will get the OH, and the N will get the H. All right, and you see that this would have been another amide here. You would have another NH here. And so you're going to hydrolyze that. This would get the OH, and this would get the H. And this would have a carbonyl, and you would hydrolyze that, and this would get the OH, and this would get the H. And what you see is the same molecule. So this molecule and this molecule are exactly the same. And so this does not have two monomers. This only has the one monomer. So you have a polymer made from just the one molecule, and that is your NH2, CH2 sub 5, C double bond O, OH. And if you would write it again with this second one, you would write exactly the same thing. And so this simply polymerizes by itself. That molecule, many of those molecules will polymerize, and it will form nylon 6. Right. 7. Which of the following amino acids has a non-polar side chain? All right, so these are good examples here because these are the ones that are exceptions to the most. All right. So nonpolar, any R that has carbon and hydrogen only. All right. So if your R only has carbon and hydrogen only, they are nonpolar. There are a couple other nonpolars. All right, but all of the R's that have carbons and hydrogens only are nonpolar. That is not an example in 2457. And when you look at polar, all right, so here, if R seen, then they're polar. So if your R group contains O, it is polar. So all R groups that contain O are going to be polar side groups. All right. So the two examples, your R group for the first one is methionine. It is a CH3SCH2CH2. All right. And so this is a very good problem because they give you cysteine as well. It's the two amino acids where the R groups contain sulfur and CH2. So that's the R group. So when the sulfur is between two carbons, then it is non-polar. If the sulfur has a hydrogen attached to it, then it is a polar. So these were, this is going to give you, I forget how many, most, probably 15 out of the 20. You can get whether they're non-polar or polar. If the R group contains O, it's polar. If the R group only contains carbons and hydrogens, then it's non-polar. There were a few exceptions to this, and so here are two of them. So if you have the sulfur between two carbons, that is a non-polar side chain. If you have an SH, that is a polar side chain. So when we go down to 2458, all right, so again, it's the same question. We're just looking at the R group. We want to know if it's polar or non-polar. The first one has CH2 a bunch of times, 1, 2, 3, 4 times, CH2 sub 4, and then NH2. This is an amine group. This is the most basic organic functional group. This is a basic amino acid. And so if you are acidic or if you are basic, you are always polar. And so that is polar. If you are an acidic amino acid or a basic amino acid, then you are definitely a polar side group. The other one fits into our class of the usual. This one did not fit into the class, but it did. You should know your 3 basic amino acids. They are all polar. You should know your 2 acidic amino acids. They, again, are both polar. Here you have CH3, CH, CH3, and CH2. So this is simply carbons and hydrogens only. If your R group contains carbons and hydrogens only, it is a non-polar. All right, so knowing that the side group, if it contains only carbons and hydrogens, non-polar, you're going to get most of those covered. And if it contains oxygen, it is polar. Again, you would get most of the polar ones covered. But there are a few others that you, like the cysteine, like the sulfur ones, they contain sulfur. So you have to know the one that has a sulfur between two carbons is nonpolar, and the sulfur that's connected to a hydrogen is polar. So that you just have to remember. All right. 65. Name each of the 3 major constituents of the nucleotide adenosine 5' monophosphate. That's just AMP. Adenosine monophosphate. All right. So this is not deoxy, so there's not a D in front, so it is a ribose. All right, so you have the sugar ribose. If it is deoxyribose, if it is, it says deoxy in front of it, or it has a D in front of the DAMP. You've got a 5' phosphate. And your nitrogen base, all right, off of the 1 prime, you got your 1 prime, you got your nitrogen base. And in this case, it was adenine because it said adenosine. All right, so for your nucleotide, the nucleotide, you're going to have a nitrogen base. You're going to have, well, for RNA, you're going to have ribose. For DNA, you're going to have deoxyribose, where your carbon, your 2' carbon will not have an oxygen if it is deoxyribose. And then off of your 5', you will have a phosphate. And your ribonucleotides, these are monomers of RNA. Your deoxyribonucleotide is the monomer for DNA, and they will link between the 3' hydroxy and your 5' phosphate. And they lasso water, so the OH of the phosphate is a PO4, and so it is the lasso of water between the 3' hydroxy and the 5' phosphate of 2 ribonucleotides or deoxyribonucleotides. All right. 72. All right, so we have a polymerization. We have NH2, CH2, and some number of carbons, some number of CH2s between the two NH2s. And that is going to react with the other monomer, a dicarboxylic acid, CH2 sub 8. All right, and so you're going to get the lasso of water. So when you lasso water, if we show the two H's, all right, so we lasso the H of the N and the OH. Again, if we show the two H's, we lasso the H, we lasso the OH, and so our polymer is NH, CH2, some number of carbons, NH, C double bond O. Again, this is a polyamide. We are forming the amide functional group. CH2 sub 8, C double bond O. And so we have a large number of these, a large number of those. We find a polyamide. All right. So we want to know, the question is, what is the value for N? All right. And so we did a analysis of this polymer and found that we had 66.1% carbon. All right, when you have percents, I will always assume 100-gram sample, because then your percent just turns into grams. Assume any size sample you want, 100 just converts the percent to grams. I always do the 100-gram sample. All right, molar mass of carbon, 12.01 grams per mole. We will get the moles of carbon. So we are just doing an empirical formula. You have then 10.3 grams of hydrogen divided by the molar mass of hydrogen, 1.01 grams per mole. All right, and then we have 11.0% nitrogen, so that is 11.0 grams of nitrogen, and 14.01 grams per mole of nitrogen. And finally, we have a 12.6% so grams, 100-gram sample of oxygen, and then we divide that by the 16.00 grams per mole for your oxygen. All right, and when you add those up, you get 100% or 100 grams. All right, so when we push the buttons on the calculator, all right, I didn't do it to great accuracy, so 5.5, I just rounded it here, 10.3, 0.78, and then 0.78 again. All right, so this is your moles of carbon, this is the moles hydrogen, this is the moles nitrogen, this is the moles oxygen. Now remember, when you're doing empirical formula, you then divide by the smallest number that you obtain, and that is a tie between your nitrogen and your oxygen, and that was 0.78. And so here we have 1 mole of O, we have 1 mole N, hydrogen, we have 13 moles hydrogen, and carbon, we have 7 moles carbon. All right, so the empirical formula is C7H13NO. The empirical formula is C7H13NO. This is empirical. All right, but here we see that in one of these units, we have for sure 2 nitrogens and 2 oxygens. So we know that we have to multiply this by 2. So now we have C14N26 N2O2 when you double that. All right, so we see we have 2 N's, we have 2 O's. We can count, is an H, it's not N, it is H, 26. We can count the H's. All right, we have 8 times 2, that is 16 H's here. We got 1 there, and we got 1 there. So we have a total of, right now we're looking at 18 H's. Carbons we look at, we have 8 carbons, 9, 10 carbons. We have 10 carbons. All right, so right now we have 18 hydrogens and 10 carbons, but we have to have 14 carbons and 26 hydrogens. So the easiest one to look at is the carbons. You have 10, and now we know that we have to have 14. So this N value has to be a 4. So N is equal, that N value there is a 4, and that would give us 14 carbons. So now we would have 14 carbons, the 10 over here plus these 4. And now we have 8 more hydrogens. So 18 plus 8 is the 26. And so you would find your N value by getting the empirical formula and then looking at your polymer and knowing that you have 2 N's and you have 2 O's. And so you would have to have 2 of each one of those. And so you had to multiply through by 2. And then that tells you 14 carbons. And that means you had to have 4 CH2s. And when you check your hydrogens, that comes out to 26 as well. (2474) aspartame, low-calorie sweetener, is the methyl ester of a dipeptide. Here is the structure. So we got HO, double bond O, CH2, CH, NH2, C double bond O, NH, CH, NH2 with the benzene ring, C double bond O, and then your CO and your CH3. All right, so here again, you have your amide. All right, but when you have your amide bond, remember that this bond is the amide bond, but when you talk about amino acids, it is called the peptide bond. All right, so it can be called either one. It can be called the peptide bond or the amide bond. All right, so if you have a polyamide, you have a polypeptide. All right, so here we are going to split with water, hydrolysis, put the OH here, and we put the H here. And so we see that the R group for this amino acid is one of the acidic amino acids. So when your R group contains a carboxylic acid, there are two of them, aspartic acid and glutamic acid. All right, so that is your R group here. All right, you don't have to know that that's aspartic acid. You do have to know it's an acid, though, and you have to know it's acidic. Here, this is so of course, this is acidic and also polar amino acid. This one only contains carbons and hydrogens, so this is nonpolar. And this is phenylalanine. You don't need to know the name of the amino acid, but you have to know that that's the R group, and that's only carbons and hydrogens, and that's a non-polar side chain. All right, if it's okay, so it's going to be hydrolyzed with water. Okay, so this you're going to be your two amino acids, but over here, note that it's not an amide. This is an ester. So if it was a polymer of an ester, of course, it would be a polyester. All right, this is an ester. If we want to break the ester with water, hydrolysis, again, your OH goes here and your H goes here. And so you would have your two amino acids, plus you would get your methanol as well when you did the hydrolysis. All right, so your structure, the R group here, CH2 with a carboxylic acid, and your R group here is a CH2 with your benzene. All right, so we could put them in the order this way, or we could put them in a different order where your R group, this one starts with aspartic acid and goes to phenylalanine, and we could do that in reverse. So we could have our NH on this side going to C, and now our CH2 with our phenyl group is the first one from left to right. And then C double bond O, OH. All right, so that's your phenylalanine. We're going to lasso that H. All right, and then we will then take our other NH. And now this is our alpha carbon, and our R group here is a carboxylic acid, CH2, C double bond O, OH, and C double bond O, OH. All right, and so we're going to lasso this. And so your other dipeptide that you can get would basically, it's the same, except it's a different primary structure because we're going to switch the order. And so here we're going to have NH, NH2, we just want a dipeptide, NH2, CH, and then you have your CH2 with your phenyl. Abbreviation for this benzene ring is pH. C double bond O, and now we have lassoed that water. And so now we have NH, CH, and then CH2, and then COOH. You could write it out, or you could write COOH. And then that is your C double bond O. And now you have lassoed the OH on this side. for the next one, but we just want the dipeptide, and so we will leave it as the carboxylic acid if we wanted to further polymerize it. So here you always go from the nitrogen side to the carbon side, and so now you've got your phenylalanine first and you've got your aspartic acid second. Up here you had your aspartic acid first and your phenylalanine second. And so it's just a different primary structure. You can just switch the two amino acids. All right, how many tripeptides could you make from valine and alanine? So I'll just use V and A for valine and alanine. So you can have all valine for a tripeptide. And remember, a tripeptide means that's how many amino acids. Does not mean how many peptide bonds, because a tripeptide only has 2 peptide bonds. A dipeptide here, we made the peptide bond. A dipeptide means you use 2 amino acids, but it's only 1 peptide bond. All right, so you could put all 3 could be valine, all 3 could be alanine. All right, you could have 1 valine, 2 alanines. And that's how you could do that one. Or you could have 2 valines, 1 alanine. And that's all you can do with valine and alanine. You have all of them the same, or you have 2 of them the same. And that is it. So there are 8. There are 8 possible tripeptides when you use valine and alanine. Now, if valine and alanine have to be in all of them, well, then you only have 6 that have tripeptides that have both of them in it. But if you could just have all valine and alanine, if that is included there, then the total is 8. And that is it for the homework. So, all right, going to look a little bit at our nucleotides. All right, so when you look at your nucleotides, again, they are going to have so your nucleotides, which is the monomer of RNA and DNA, you're going to have your base at the 1'. That's where you're always going to have your nitrogen base. Your 5' is going to have your phosphate. Your sugar is ribose or deoxyribose. So you're looking right here. If there are 2 H's on this, now you're looking at DNA. If one is an H and one is an OH, then you're looking at RNA. The linkage that we're going to see is going to have an OH here, and you're going to have the lasso of the H here, and one of these O minuses I will put as an OH, and I'm going to lasso the OH from the phosphate and the H of the 3' hydroxy to link my monomers. All right, so and again, uracil and thymine. All right, so DNA only, RNA only. If you look at their structures, they are different by a methyl group. So thymine has the methyl group here, and uracil does not have the methyl group here. So a very minor structural difference between thymine and uracil. All right, so again, when it says, am I looking at RNA or DNA, and they have the picture, this is where you should be focused. So this is RNA. And when you remove that oxygen, now you're looking at deoxyribose. You remove the oxygen off of carbon number 2. And so you're not supposed to recognize the bases. You're not supposed to recognize anything else to tell the difference between RNA and DNA, just at the C2 of the sugar. If it has the OH, you're looking at RNA. If it does not have an OH there, then you're looking at DNA. All right, and so you need to know what a ribonucleotide is. Again, 5' phosphate, 1' base, and a ribose sugar, whether it's deoxyribose or ribose, RNA or DNA. All right, so again, when you are going to link your phosphate, all right, to make the monomer for RNA and DNA, again, you're going to lasso water, the OH from the phosphate and the H from the 5'. So this is your monomer, and this is not showing an OH at the C2. So this is a DNA. So this is a monomer of DNA because they are not showing an OH there. All right, and so when we are going to take ribonucleotides and polymerize them, we're going to take this H, and again, I'm going to make one of these O minuses an OH. So it's going to link your 5' phosphate with your 3' hydroxy. All right, and so again, if there's an OH here, you're looking at RNA. If there is an H there, then you're looking at DNA. All right, and so again, a question here is, this is a monomer. Is it a monomer of RNA or DNA? Well, you look right here. This is a monomer of RNA that has the oxygen on the 2'. So this is a monomer for RNA. You're not recognizing, well, this base is the same for both of them. That's the only difference between the two, is the OH here. Now, if we had thymine and uracil as the base, then we could know the structure of that. You don't need to. All you look at is the C2 position. See if it has an O or not an O. Again, we're looking at a monomer for RNA. All right, so here's where we're going to link it. So here is one deoxy, no OH shown here, deoxyribonucleotide. All right, and so we're going to, again, I always put an H here. All right, and I will lasso water the OH from the 5' phosphate to the H on the 3' hydroxy. And that's how I will link my two nucleotides. And this is called a phosphodiester, all right, because you have a P double bonded to O, and then now you have an O with a carbon group, which we put as R. Down here we have our O minus, and then on the other side we have another OR. So when you look, if you pretend that P is a carbon, that is an ester, all right? All right, so that's an ester functional group if that's a carbon. So this is a phosphoester, but it is a phosphoester on that side and on this side. And so that's why they call it a phosphodiester. All right. All right, so again, every time you are linking this, again, this is RNA. You know that because of this, or if they say you have uracil, then you also know you have RNA. But when you have an OH on the C2 position, you know you have RNA. All right, again, you're linking the 5' phosphate to the 3' hydroxy. You have lassoed water. So you had your P, your OH, you had your O and H. You lasso your water, and that's the PO bond that is formed right here. and now you've got a phosphodiester, OR here, OR there. All right. All right, so your DNA, it's going to look exactly the same, except you're going to have thymine, which means now you have a methyl group here instead of uracil, which doesn't have a methyl group there. That's not what you're looking for unless they label it as thymine, then you know it's DNA. But what you're looking at is the C2 off of your sugar. If those are both H's, you're looking at DNA. All right, so they link exactly the same. All right, it's the 5' phosphate with the 3' hydroxy. All right, the phosphate and the 3' hydroxy. Again, you're lassoing water, and that forms your O bond here. Again, that is a OR. It's a phosphorus double bond O. It is a phosphodiester. And that's how you link it. So your RNA and your DNA link exactly the same. Again, your DNA has thymine, and your DNA, what you're easily going to pick up on is the C2 does not have an oxygen. Okay, and so here is the one problem on the test that, or on the homework, that said, what about your hydrogen bonding? So between adenine and thymine, or adenine and uracil. Again, the only difference is your uracil is going to have is going to be missing this methyl group, which doesn't change the hydrogen bonding at all. All right, and so it has adenine and uracil have the exact same hydrogen bonding as adenine and thymine. All right, so you have just 2 hydrogen bonds for your A and T, so that's why we write it ... with a T, so that's showing the 2 hydrogen bonds. And your GC, guanine cytosine, that's why you draw it with the 3 dots, because it has 3 hydrogen bonding interactions. And so it is held much tighter. This is a much stronger force, 3 hydrogen bonds versus your 2 hydrogen bonds. So GC is held together stronger than your AT is held together. All right, and so I think everybody knows that your DNA is the double helix, and it's held together. Again, they're showing the 2 hydrogen bonds, the 3 hydrogen bonds, the 3 hydrogen bonds, the 2 hydrogen bonds. So that's why those dots are there. They are indicating the hydrogen bonds and actually indicating how many hydrogen bonds. All right, and so do not miss the easiest problems on the test when you are looking at going from a DNA replication. So you are going DNA to DNA. All right, so make sure that you have DNA to DNA. You got G going to C, and you got T going to A, and A going to T. So A, T, G, C, T, A, G, C, G, C, T, T, A, G. Okay, it should be that simple and fast. All right, so that is it for today. That is on Monday at 8 o'clock. We are going to be in here, yes. Yeah, so it's going to be in this room. It's the lecture room where we take our final. That's going to be outside at the tent. Yeah. So it is going to be completely outside. And that'll be the usual 5:30 pizza. I guess the usual. Yeah, it might be a little later. So I'm thinking 6 to 8 or something, or 5:30 to 7:30, or I don't remember what I was thinking. But I'll put an email out. I'm going to talk to Deskins and see what time she wants to do it. But it'll be similar times. But the demos aren't going to take very long. So and sometimes we lose patience. So it's like if it starts at 6:30 and we started eating at 5:30, we might be done by 6:30. But anyway, I will send out an email on that. Probably, I'm going to guess pizza will be the usual time at 5:30, and then probably the demos will probably start at 6, or pizza at 6 and demos at 6:30. I got to talk to Deskins and see what She think because we can eat while doing our watching, so it's not like we have two separate things that have to be done separate.